Nevertheless, it serves for explaining a number of interesting topics. So it has a standard metric, and we want to have a nice operator there. And the most obvious operator is the Gauss-Bonnet operator, which acts on the differential forms, which I denote by lambda. And this is a closed subspace of the L2 forms. And this operator is self-adjoint if we close it up. So I could also say essentially self-adjoint, and it has a discrete spectrum. Which is explicitly known. Actually, we can check everything we want just by writing down the solutions for the forms, which all derive from the eigenspaces of the Laplacian on functions in this case. But anyway, we can decompose the space, S2, as a sum, a Hilbert sum of the eigenvalues of this operator, so where n goes from minus infinity to plus infinity, because this is a first order operator, which is not semi-bounded. So lambda n goes to plus minus infinity if n goes to plus minus infinity. And we normalize this by saying that lambda 0 is equal to 0. So this is enough good description. And of course, S1 commutes with its operator. And this implies that the ED of lambda n are S1 spaces. So we have unitary representations which actually are nicely structured. And this is basically the Peter-Weyl theorem, showing that every Hilbert space unitary representation of a compact group is decomposable into irreducibles. And now you could ask for the multiplicities of groups. So I would say the multiplicity of S1 or any other group, S1 belongs here, and here is an eigenspace, is the number of times the irreducible representation rho appears, which is essentially, no, it's equal to the dimension of the S1 invariant maps from the representing space. V rho is a finite dimensional irreducible representation representing rho into the space ED of lambda n, which could be any other space. So these are the S1 equivariant maps, which the number of which gives the multiplicity of the space of the representation rho in this space. And this is very often interesting, and especially interesting for the kernel, which is basically the homology of S2, which is not so difficult. And especially here, we see immediately from the homotopy axiom that the multiplicity of any representation in the kernel is, of course, 0 if rho is not the trivial representation, and it's the dimension of the kernel if rho is equal to the trivial representation. So you could say it's actually not quite interesting to study this any further. Of course, this changes for finite groups, or rather disconnected groups. So that's quite interesting. So in this case, we would call mu rho of the index of D. So now if we look at the representation ring, then we can form the difference of two representations. So we can talk about these two things. And this is actually the index of D plus minus the multiplicity in the kernel of D minus. So what is this? I mean, D commutes with a certain involution on the space of forms, namely the multiplication by minus 1 to the power j. This is an anti-commutation, so D splits under this involution like this, and of course this index need not be 0. So in our case here, this is just the Euler characteristic. That's actually true for any manifold, not only in this simple example. And an interesting fact is that this number, this integer number, can be written as the integral of the Gauss curvature. It's the Gauss-Bonnet theorem, which is well known. However, why this integer can be decomposed in this way is still, in a way, mysterious. I mean, there are technical explanations. There's no really deep explanation for this, or at least it's only emerging. So now if I add this S1 action here, which commutes with all the data I have introduced, then of course we are forced to look at the orbit space of this x1, this action, and it's clear that this is an interval with two endpoints. So this is already the simplest form of a singular space because it has boundary points. So it's strata of two different dimensions. So the open interval with the one-dimensional thing and these 2 points. So this is already quite interesting. So if you look at this problem in general, you are interested in determining what the multiplicity of any irreducible representation of the group in this kernel may be in this weighted sense. Yeah, so now we take an arbitrary Riemannian manifold, let's say closed and oriented, and then we want to generalize this, and the nicest class of operators is the class of Dirac operators, which I describe like this: to have a complex vector bundle E over M, which is graded, so alpha E is just an involution on the bundle, and which carries a Clifford multiplication. So this I explain in a moment, just a little bit, and also a connection. And these things have to have certain compatibility conditions. For example, the Clifford multiplication is odd. And this has a complicated compatibility relation with the Clifford multiplication. So let's say here we have to put it like this. We take two vector fields and compute the commutator. This is Clifford multiplication by the Levi-Civita derivative of these two vector fields. That's a very natural condition. It's the deviation from Clifford multiplication being parallel. And so we require this, but very often it's not satisfied. Now the Clifford multiplication let me just describe it on the exterior bundle, which we used a moment ago. Then this is just the wedge multiplication by the one form associated to the vector field by the metric minus the interior multiplication with the vector field. And this, all this is very well known, of course. It's characterized by the fact that the square, so this is an endomorphism on the vector bundle, and the square equals the norm of x squared times the identity, of course, the norm formed in the metric on the manifold. Now, if I have these data, I can vary the metric. I can actually, for a closed manifold, take any Riemannian metric, and you see that this Clifford multiplication is functorial in the metric, right? At least for those bundles which satisfy these compatibility conditions, they are always locally generated under tensor products by spinor bundles. Of course, there could be several spin structures. So as E tensor sum E equals S M tensor sum coefficient bundle. And in this case, there is a general index formula the famous formula by Attia and Singer that the index of d plus with respect to the involution alpha equals the integral of a certain differential form, which is very analogous to what I wrote there for the two-sphere, namely so-called a roof genus times a Chern character, which is usually written as E over S, meaning you take the square of this connection and then the so-called twisting curvature. The first part of the curvature generates this part, and the second part generates this term. So it's a very nice formula. Again, shows you this amazing fact that this integer can be decomposed into integrals. So this a roof is quite telling because it reminds you of the Fourier transform, and this may be the most basic fact which is behind this. Okay, now we take a group G, a compact Lie group, acting by isometries. And commuting with the Dirac data. And so with the operator D, which we will always consider on, let's say, compactly supported smooth sections of M with values in E. Because D can be written in terms of the data in this well-known formula, where EI is the local frame for the tangent bundle. Now the question is, so we have this formula, and we want a formula for the multiplicity so mu rho index D plus for rho a representative of some irreducible representation, but not just any formula, but a formula which is analogous to this one. This is the problem. Because this would relate the multiplicities to the geometry of the orbit space. So this is because it would relate mu rho of index d plus with the singular space. Yeah, I like to write this m lower bar because there are so many things which you have to think about. This is a singular space, as you can see from this example, but of course, if you have more stuff, you see more such things. So we have to have a look, we can leave this, at what people have done, because there's actually a huge body of literature on this problem, various aspects of this problem. So let's say some lines of attack. What have people done? Well, you have to rewrite the multiplicity you want in some other terms. So I think I wrote it this way. I always mix up. I will put the row also there, but this differs only by a constant later. So what is it? Well, the simplest thing you can think of is that you use the orthogonality relations of the characters. So you take the character, the virtual character of index d plus at the point G, and you multiply this by the conjugate of the character of G and integrate over G. So this is the bi-invariant normalized integral, which exists on any compact Lie group. So the integral is 1. This is the integral over G. And this gives you exactly the multiplicity, the weighted multiplicity of this here. So let us recall for a moment that this is actually the character of d plus minus the character of the kernel of d minus at the point G. And you can rewrite this very nicely in the following way. I mean, because this is the odd homology of the space, this is actually a Lefschetz number, right? This is the Lefschetz number of G acting on the homology. And so this was invented by McKean and Singer, that you can write this as a trace, over the space L2 of M E. So you put in here, to get the minus sign, the involution, the action of G, and you multiply this by the heat kernel, or the heat operator generated by D, and integrate. Why is this? So if you make t equal to 0, then you get exactly this here, right? Because then all the eigenspaces disappear. But if t is positive, you differentiate this with respect to t. So you get out the d squared, which commutes with G, but d anti-commutes with alpha. However, if you have it here, you can also write it here because you have a trace, and so it's 0. So this was the fantastic discovery, which also tells you, because this trace has an asymptotic expansion, all the stuff which has negative powers must cancel because this is an integer, known a priori. These are the magic cancellations which McKean and Singer discovered, and they say for some reason, which we do not fully understand maybe now, but there are good techniques to apply it. All this stuff localizes on the manifold into nice geometric things. Actually, in giving this expression, where you actually use that d squared under a certain scaling degenerates, if you like, to a harmonic oscillator with curvature terms, and this gives, by the Mehler formula, exactly this element. So this is the analytic explanation for this. And this also explains why most people actually looked at this stuff here by fixing G and then expanding traces. There's a lot of work about that, which gives the complete answer to the problem here for finite groups. Because if you can localize this for a fixed G, naturally on the fixed point sets of G, you also get a finite sum over these wildly varying fixed point sets. And this is your answer, where you see some such characteristic form or restricted to the fixed point set, plus some information from the normal bundle, because the fixed point set is somehow put in, and this is what is interesting for the singular index theory. Okay, yeah?
I have a stupid question. What do you call exactly the character of the kernel of D+?
This here?
Yes, yes.
So this is the character of this G space. Okay, it's the trace of G over the kernel of D+. The kernel of D+ is invariant,
Yes.
because G commutes with D and with alpha. Okay? And this is a virtual character. So it's an element of the character ring. And therefore it can have integer values, not just non-negative. So what is do you still have a problem?
Yes, I still have a problem.
With what?
So you say, okay, so G acts on char D+,
Yes.
and you take the trace of that action.
Yes.
And that's it.
That's it.
Okay.
Yeah, very simple. Okay, so another thing is now actually a very nice formula, which is -1, which is more analytic. Sorry, the integral disappears. Now, in this formula, there is a projection hidden. Maybe I put the times the projection P rho here. So this is taking place in the L2 space, L2ME, where this operator acts. And now we put there an orthogonal projection. And this needs a little explanation, but for those who know representation theory, this is not difficult. S is now an element of our space, and we apply P rho to it by taking here the character of rho and applying G to the element and integrating. This formula is maybe less well known, but certainly to those who do group actions. The reason is that this times this is an idempotent in the convolution algebra of G. Okay? So if you compute this, P rho squared is a projection. This is what it means. And then you see that it, well, I should maybe explain something. What means the action of G on an element of L2 evaluated at some point P? So this is G applied to the section at the point G inverse of P. Okay, so you can check this is the left action, but you have to keep this in mind. This is not, so first, here you act on the vector bundle, and here you act on the manifold. The action on the vector bundle covers the action on the manifold, so the projection of the vector bundle is G equivariant. That is the the definition. Now, what is the space which we get as the image of this projection? So P rho of L2. Well, this is the space whose G decomposition consists only of the representation rho, and no other orthogonal invariant space to this one contains the representation rho. So it's the rho isotypical subspace. This is all elementary, but needs to be understood. Yeah, this means, maybe I go here. Is this visible from everywhere? No? It is, yeah. So I introduce the operator d rho, p rho d, and by construction, it's extremely easy to check. D commutes with p rho as an unbounded operator. That means p rho maps the smooth section into itself, and on a smooth section it commutes with d, okay? But this means that this operator is also essentially self-adjoint on the image of the smooth sections, and is a discrete operator. So it's also discrete and odd in the sense as I used before. It anti-commutes with the involution. And so we get this nice representation. And so now you think probably the multiplicity we look for is connected with this operator, and this is actually trivial to see. The index of d rho plus is isomorphic to, now this is the multiplicity. Don't mix up these two, tensor the representation space. Just the number of times this space occurs in here. Of course, weighted by. So it's interesting to study this operator, but d rho is singular. In a sense, I will make precise immediately, but I want to go back to these formulas. So we had here the character formula, which is very much used. We used McKean-Singer trick. We introduced the projection. And now we can, of course, do something else. Then we will just plug into this formula. This is the easiest. Take the heat operator of this. This is an operator with a smooth kernel if t is positive. Of 2 points, valued in 2 points. The group action is as I explained. And so what we get, the trace becomes an integral over m of the pointwise trace. So that's the trace in the fiber p of the vector bundle. Okay, of what? Well, we need this here. This we know. We need the application of G, well, which is now applied to, in the obvious way, to an endomorphism of the bundle, which has to be taken at these 2 points. And then the character comes, and then dg dp, which is a formidable expression. But of course, this is here you see the main fascination of the problem. So the kernel at the point qp maps the fiber at p to the fiber at q. And this here maps p to g inverse of p to p. So this thing is an endomorphism at P. So this is well defined. Interesting point. And we know the heat kernel is regular for Q not equal to P, but if the two are together, then it has a high singularity, delta function like. So what we need to study is the strange set G, which consists of these points, Gp equal P. And the whole trouble is that this is not a nice set in the sense of any pseudo-differential or Fourier integral operator type. I mean, this is a very bad set, a very bad set. So that means if you have an asymptotic expansion of this, a point-wise asymptotic expansion, maybe at the points even, you cannot integrate it over G over M. Okay? This can simply not be done because the singularities move around and change their type. They're not the same type. So this is why the problem is really difficult. And concerning such formulas, I just mention a few people who have contributed, namely Donnelly, Harold Donnelly, Peter Gilkey, for the pointwise expansion. Attia Siegel, the index formula for finite groups, and Attia for certain torus actions where we have at least commutativity. And then for the full expansions, I mention Berlin, which has nothing to do with the city I'm living in, and Michel Verne, very sophisticated work, but oriented at representation theory, for example, by reproving Kirillov's formula as a local index formula. Okay, so far so good, but we have more simple-minded ambitions, and the time is running, yeah. So the next thing I want to briefly explain is the case of one index type, one orbit type, sorry. So this is belongs to the theory of transformation groups. If a group acts on a manifold, then you have, of course, the orbit, Gp, and the isotropy group, G sub B, isotropy group. And the orbit type is the conjugacy class of the isotropy group. And for a compact group, there are only finitely many. K is equal to the number of orbit types. It's called the complexity. And G0 is the smallest isotropy group. Smallest in the sense if I take any other isotropy group, then this is conjugate to a subgroup of the other. So they become larger. And G0, M0 is equal to P, such that the isotropy group is equal to G0. This is very important is an open dense subset. And if you have only one orbit type, then the orbit space is smooth, which I write like this. But not compact in general. So in the case of the two-sphere, you just take out these 2 points. Then the principal orbit, this M0, has as orbit space the open interval. It's the sphere minus the 2 poles. But there are 2 singular points completing this to a compact metric space, let's say, or to pseudo-manifold. And it's quite important to study this case. Yeah, put this here. This here now. Oh, can probably not use this. So if we have this situation, so M is equal to M0, then the orbit map, let me call it like this, with a fibration and then we can, this is a little work, but I just explain it. We push the data to the orbit space. So what does it mean? So we get a bundle over the orbit space with fiber. Now this is not a finite dimensional vector bundle. The fiber is the L2 space on the orbit, which is a submanifold, into the bundle E restricted to the orbit space. So this is a infinite dimensional bundle. So we have a Hilbert bundle. It has a natural Hilbert-Dirac bundle structure, which satisfies nicely all the axioms we want if we adjust the connections. That is always the problem, that whatever connection you take with these compatibility conditions, it computes for you the same thing. But you have to play with the connection in a very subtle way, especially in this case of Hilbert bundles. You meet things which Bismuth first introduced is the famous Bismuth superconnection. So we have this, and we get the Dirac data. So we get an alpha, which is easily inherited. Likewise, the Clifford multiplication, which we now restrict to horizontal vectors. Yeah, so it's like the lifts of vectors on this space. Well, here we have to think. So to find a compatible connection is not so simple. But then we also have a Dirac operator, so which I now have to write DH, D lower bar H, because it means horizontal, such that D, now we are upstairs, is this a lift of this operator plus a lift of the vertical operator, and the lower bar is the lower bar H, which is the real Dirac operator associated to this, but unfortunately not completely, but this vertical operator comes in addition. So if you study the index problem on a compact manifold which is fibered, and you introduce the fibration, you see that if you really want to understand what this index does and how it localizes, you have to understand the index problem on Hilbert bundles, which is quite strange, but this is what starts to explain why we have these localizations. So for us, this means that this operator looks formally the same, but it is rather bad, because now we add an operator which is also a first order differential operator. Namely, if I restrict dv to some of the fibers recall are the orbits, is the orbit space, is the Dirac operator naturally associated to the orbit. Again, this is a subtle interplay between the connection restricted here and the restriction connection on horizontal vectors. This works out nicely. And we are ready to despair, but remember, naturally associated to the orbit. So you restrict the bundle to the orbit, you restrict this and this, but here you have to play. And so what you put away here is used here to make this the compatible connection. And this implies that our original Dirac operator is unitarily equivalent to this operator because the L2 spaces are isomorphic. This is just the Frobenius theorem, yeah? Isometric actually. Okay, now I take the row. Yeah, putting row. So this I explain briefly. Putting row means that I have to apply this projection. Now the projection, remember, we have it somewhere, was just integrating over the group. So means if I put in a section of the L2 space, it means integrating values along the orbit. The projection stays on the orbit. So that means that the representation rho on this orbit space, where E becomes a homogeneous bundle, is just the projection induced from the restriction of rho to the isotropy group. This is the so-called Frobenius reciprocity theorem, here applied in the Hilbert case. And the short outcome from this is that this Hilbert vector bundle here, after projecting to rho, is a finite dimensional bundle. Yeah, and so we get gives d bar h rho plus dv rho on a finite dimensional bundle. I have too much to write. E lower bar rho. So then this is an endomorphism, so does not contribute to the index. So we can cut it actually, and we are back in the same situation. We have, if everything was closed, we get from dividing out the group, we get a perfect Dirac operator on the base with a perfect Dirac bundle. We can compute the index in the same way as before by forming these characteristic classes, now with M lower bar and E lower bar. Very nice. But of course, this is the simplest case. What you want to do in general is to apply induction on this complexity k, and k equal 1 is the case I just treated, being settled. So what do you want to do? now we have to make a choice of things to leave out. Let me look again at this beautiful, simple example. I have to somehow deal with these alien spaces here, sitting at this point. And what I could do, for example, is just to cut out these spherical caps. Then everything is nice here. I have to deal with it somehow, and hopefully I can compute it. And here I get an arbitrary parameter epsilon, which should go to 0, and I could hope that things are fine. But we must not ignore that we make a dramatic change with this manifold, namely taking out these points and making it a cylinder, right? So this has some important precursor, namely index theorems for manifolds with cylindrical ends, which I cannot really explain, but it may be known to many of you. P is Patodi, Atiyah Patodi Singer, where they discovered the eta invariant by looking at such a manifold with some boundary conditions and taking the difference of the index, which they can compute, and the integral, and saying that's not all, there's something missing. This missing thing is the spectral invariant of the boundary, which is actually a big surprise. And the question is, the price question, how can you do this and keep track of the changes you administer to this d rho index d rho plus, right? And so now I want to explain briefly the result, which is with Ken Richardson and Franz Kamber. Yeah, what do we do? So the important observation here is, first of all, I mentioned this already, what we are doing here is functorial in the metrics we use. And of the metrics you should think as being metrics on the orbit space pulled up to Riemannian metrics on the closed manifold. So any change I do there enters functorially in the Dirac constructions and does not change the index, because we are always doing this through families of Fredholm operators. Okay, so deformations, we could say, are built in. Secondly, and now this is, so to speak, the point where we really deviate from what most other people did. We take this, where did I write this heat kernel? Oh, there. Look at this integral. And now think the top thing, yeah? And now think of restricting it to a saturated set. This means a set which is G invariant. An open set. And then take the limit of the whole thing as t goes to 0. I mean, if I do this over M, I know the limit does not depend on t. I mean, the whole thing does not depend on t. If I do this for a saturated set, this is not so clear. But what one can relatively easily prove is that the limit we form does not depend on any boundary conditions which are outside of the closure of the saturated set. This depends only on the local geometry, only on the local data, which I have written down. That means, so if I want to compare this with, say, something like this, okay? If I do this, what do? I open this thing here, because it's a cylinder, make the metric here cylindrically, which I can do canonically in dependence on this metric. And the result is a manifold with one orbit type. Of course, the index cannot be the same. There is some deviation, which is exactly the Atiyah-Patodi-Singer deviation, which is in terms of the equivariant eta invariant, which I don't have time to write down now. This manifold is not compact, which we don't like, so we simply double it. And then the integral enters here, the integral of the characteristic form. It's just 1/2 of the integral over this, okay, because the involution is orientation reversing, but the orientation sits in the volume form. So we can work with this guy. And this guy now has a complexity which is 1 lower as the thing we started with. And now we do the same thing with minimal strata, which are closed things. We blow them up or desingularize them by taking a tubular neighborhood, making it a cylindrical boundary. This is a perfect canonical construction and leads finally to something like this, that the index we are looking for, index d rho plus, for any irreducible representation rho, can be written as a complicated sum, where now we have to take 2 integers jk, because now we have to consider the components of the singular strata independently. We cannot, in the definition I gave, or I hinted at, this is, and there's also another parameter, L. So J is counting the complexity, the isotropy types, and this is counting the components, and this is counting an unavoidable decomposition of the bundle, and this I don't explain at all. So here we have the complexity at step J, and in this way we get a new set, but each component in this process, I continue it until only a closed manifold with a group action with one isotropy group is left. And in the process, I have created such a desingularization for each component. Yes, but it's a small submanifold. The integral has so many doublings as the complexity tells you, and so you have to do this, and then you get the reduced Dirac integrand. So we really do this over the orbit space, which is a manifold, but a manifold with boundaries, so the integral has no chance to diverge. Okay? And then, of course, there are these contributions, these eta-type contributions, and I just write it like this, eta-type contributions, with the same indices, kj. Yeah, so this is the final formula, which looks quite complicated, but it is completely explicit in each step. Needs only a little more time. What I said before is enough, plus some explanation of the eta invariant to give these explicit forms, where, however, this Frobenius type argument on the tubes, which you need, is more complicated, because now we have to split more carefully the bundle between the horizontal part and the vertical part, it is quite combinatorial, quite complicated, but on the factors, it really works the same as for the single isotropy type. And so you have, for the first time, we must say, no matter what, for this class of operators, a complete local description, or semi-local if you like, but it is local in the following sense, that the data which determine these eta functions are completely determined by the original metric. Okay? And for example, you see something which was not known. If all these orbit spaces are odd dimensional, then the index is 0. This is the generalization of the Atiyah-Hirzebruch famous formula that on an odd dimensional compact manifold, every index is 0 of a differential operator. And this comes here the same, was not known in representation theory so far. I mean, of course, in the end, you want to see this even more functorial in order to see what you need in a general case. This, yet now seen from the point of view of pseudomanifolds, is a very special case, because the tubes you form have spherical fibers, which is an enormous simplification. Actually, one part of this final proof is that you, how should I say this? Actually, you can reduce the final decomposition here to this case by computing explicitly for any sphere with a standard metric the difference in indices from this thing with Atiyah-Patodi Singer boundary condition and this here, which is exactly the kernel of this fiber operator, dimension of the kernel, which is a nice result in itself. And you are always dealing with operators and eta functions which have only integer eigenvalues. So it's really a number theoretic thing which occurs here, which is not surprising because you have so much symmetry. But in general, you must be absolutely clear about the fact that this fiber part will become more difficult. And what is the right tool here? This is what we really want to see. Yeah, so in order, I mean, there are almost, I mean, I think there are very, very few, maybe only one, local formulae in the case of two singular orbits or two singular strata for a pseudomanifold. Yeah. Well, that's about it. Thank you.
Thank you very much.